Hello, welcome to the third and the final part of inventory optimization. In the previous two videos, we had covered what are the mandatory inputs in terms of master data that are required for inventory optimization, what are the significance of each of these attributes, and in the second video, we have covered what are the kinds of variabilities that inventory optimization takes into account, and based on those input, how it generates safety stock at a particular location product combination. Now, in this video, I am going to cover you how inventory optimization runs, what are the parameters, and how to configure the inventory optimization profile, which is very similar, to SNOP and heuristics, wherein we can give a lot of parameters to control how inventory optimization works. Currently, what you are seeing in my screen is an IO profile wherein we have multiple inputs to control the behavior of the inventory optimization. So, if you pay careful attention to the screen, you will see that I am into the screen of inventory planning profile wherein I have assigned a particular planning area, and inside that planning area there are multiple parameters that we can give under general information, profile parameters, and administrative information is something which saves who has saved the inventory optimization profile before. So inside the profile parameters, what you will see is the planning horizon, which determines for how long in the future the IO optimization is going to run. And the optimization horizon determines out of the total horizon for how many periods the inventory optimization is going to run. Apart from the inventory optimization horizon, anything that is outside the horizon, IO doesn't work with constraints and input parameters and generates safety stocks without taking any other constraints into account. The second most important thing is the forecast error. The forecast error, we can give it in dynamic lags, where we can set up lags, CV over interval, and fixed lag. In this example, we are not using any lags, and hence we have selected the option fixed lags for the purpose of this demo. Then comes the part of the inventory storage. In inventory optimization, we can define storage resource and assign storage resource in the master data location product resource, from wherein inventory optimization can identify what are the resources, what are the restrictions and constraints of storage for a particular resource, and based on that it generates safety stock recommendation. But at this point of time, we are ignoring the capacity constraint, and hence we are selecting it as ignore, and by default the storage penalty cost we have selected as variable. Inside safety stock, whether we want the min and max safety stock in the location master that we have shown, whether we want to consider it as not. So if we select it as consider, then the min and the max stock that we have defined in the location product master is taken into account. And the optimization constraint, we have based the optimization constraint based on the target service level. Here we have the option to select the maximum safety stock input, but generally in most of the cases we set the optimization constraint on TSL. Very important thing to understand is this additional parameter where we have the option called loop handling. In a complicated network, you might come across cyclic TLANs, which means a product moving from location A to B and vice versa. Whenever these types of TLAN comes, it is considered as a cyclic TLAN and we get an error in supply planning. But IO has the capability to identify those loops or cycles and accordingly remove them and do the inventory optimization by removing those cyclic TLANs. The next option is consider the same internal service level across all components. While discussing the attribute minimum ISL, we have set the minimum ISL to 0.75 for everything. If we want to save or consider all internal service level are same, then we can select it as yes, or we have the option of selecting it as no. In that case, we have to define different minimum internal service level based on different product criteria. But at this point of time, in order to make it easy for us to understand, we have treated all ISL components to have the same ISL. And this decimal is to avoid generating safety stock in decimals rather than we want to round it up. So these are the primary parameters that we can give in the inventory optimization planning profile so as to control the behavior of how the IO runs. So once that is done, we are done with the inventory optimization planning profile. Now it's time to take a IO run. Now before we take a IO run, there are few things that we need to understand. So if you go to run and go to inventory optimization or inventory planning advanced, you will come up with multiple functions. One is global stage multi-calculation, calculation of target components, the decompose which is going to go away soon, which is single stage optimization, and multi-stage optimization with target inventory components, and multi-stage network and service level protection. Service level protection is a new algorithm that has been introduced in the recent IO release or the SAP IBP release, which basically tells us if we make any adjustment in the adjusted safety stock and run the service level prediction, it is going to give us what is the percentage of the system to fulfill the TSL based on the adjusted safety stock that we have maintained. But we are not getting into all this. At this point of time, we will run a global stage multiple inventory optimization so that we run a IO across the entire network but on finished goods. Whereas target inventory component calculation works on BOM components, which basically gives results like what should be my target inventory position, what should be my target days of supply for components, and so on. So each of these function has its own benefits. So you can test it out and you can see the differences, but at this point of time I am going to run the multi-stage inventory optimization and show you how the results are coming. So for this I select global stage inventory, and just before this we have shown you how to configure the inventory optimization profile. So if you see here, I have updated this profile called inventory planning profile, and this is the planning profile I am going to use. Remember one thing, like heuristics, inventory optimization doesn't run on location product, rather it runs on subnetwork. So in this case, I will select the subnetwork carpet tile because that is what we are using in our example and demo. And I will click on to run. So this run takes between 15 minutes to 1 hour based on the number of product location combination and the complexity of the network we have. So while it is running, let us take a look how the data looks like after the inventory optimization is complete. So if we look into this screen has quite a few key figures. So this view is not a conventional view. This is a kind of a different view that has been requested by the planner so they can easily work with the inventory optimization, and based on that they can create alerts, and based on that alert they can filter based on alerts and do planning by exceptions. So that is one of the reasons we have created this, where the time period is at a horizontal axis whereas the key figure is at a vertical axis. Now if you see here, based on the demands, and here if you see, the demand is not IO demand but it is the propagated demand mean. So what does propagated demand means? Whenever I have a DC wherein I get a customer demand, that customer demand comes under the key figure IO forecast. Now that DC, if there is a shortage, if there is a replenishment need, the demand of that DC flows into the next upstream location or the DC, which is kind of a propagation of demand or dependent demand. So dependent propagated demand mean is kind of a dependent demand that flows based on the network and the transportation relationship that you have. So here, if for this product location I have IO forecast of 100 and there is a dependent demand coming from a different location, let's say 30, then in that case the propagated demand mean will show you the sum of the IO forecast and the propagated demand based on the offset and the lead time offset, and the sum of them becomes the total propagated demand mean at a particular location. So here in this case, if you see for this product location combination, I have a propagated demand of 130. My error CV is 38, or rather let's take the example of month 3 because February is almost over, so it doesn't make sense. So in month 3 I have a total demand of 175 with a pathetic error CV of 0.8. That means the error CV is very bad, and based on that, if you see, the system has recommended a proposed safety stock of 157. Now, whatever is recommended by default goes to the final safety stock unless and until planner overrides something in the adjusted key figure. So if I put something in the adjusted, let's say 200, and save it, Now you see this override is taken into consideration and the final safety stock shows as 200. So this key figure is for planner's override, and this override doesn't need to be done at a product location level. Planner can do this at a aggregated level as well, and the number will be disaggregated accordingly. So here, since I have zero point 0.8 as a safety stock, as a forecast error, hence I have a comparatively higher safety stock. If the error CV would have been less, I would have got less safety stock. And the good thing about IO is we have a cost per unit and we have the safety stock quantity, and we have standard key figure based on this quantity and cost. We can get a dollarized value of the safety stock that we are generating or the system is generating. And at the same time, we have one key figure for days of supply, which basically looks into the final safety stock and sees how much in the future this safety stock is going to replenish, and as a result of this it generates the days of supply automatically at any level, be it month, product location, week product location, or even at an aggregated level. This is not the standard IO safety days, but this is a custom key figure that has been designed to help planner show them what would be the days of coverage based on the safety stock at any level. And based on that, we can basically see what should be the coverage at a product location combination. And based on this unit and value, we can also see the dollarized value of the cost. Here we can also see what is the target service level and what is the average service level along with the PBR. As I said, PBR for most of the case is 1. So lower PBR means lower safety stock, higher PBR means higher safety stock. Few things that you need to understand, because IO is a black box, we really don't know how the algorithm works, but we know what kind of input has what kind of impact on the system. So few points to be worth noting is, if my error forecast is high, my safety stock will be high. If my PBR is high, my safety stock will be high. If my lead time is high, my safety stock will be high. The only exception to this rule is if I am having a big lot size. In that case, the safety stock recommended will be low, because in one lot size it is going to populate or generate safety stock for a very long period of time. Hence, safety stock recommendation will not be on every week, but for each week it will be higher. So overall your safety stock will be low. Now with that said, we could see based on the demand, the variability, the forecast variability, how the safety stock is getting generated. Now remember one thing, that for the purpose of this demo, we have also introduced production lead time variability, and we have also introduced location source variability. Now once this proposed safety stock is generated, by default the system gives us a bifurcation that out of this total safety stock, how much of it has been due to demand variability, how much of it has been due to supply variability, and how much of it has been due to production variability. So for that, I will take you to the next sheet, which gives you exactly the bifurcation. That, for example, for this product, let me take this product as an example. So here, if you see, for this product at month 3, I have a final safety stock generated of 107. This 107 has been generated because of primarily two factors. One is service variability, which is basically by lead time, and this is demand variability. So out of this 107, 105 has been generated because of my higher forecasted RCV. Whereas this 1.31 has been generated because of my lead time variances. Similarly, if I would have had production variances, it would have given me a further bifurcation. So this recommended safety stock not only gives you how much safety stock you need at a particular product location at any given point of time, but it also gives you the bifurcation that how much of this safety stock is because of forecast variability, how much of it is because of service variability, and how much of it is because of production variability. So that's how this inventory optimization works. Now, few things to understand and note is, as I said before, unlike heuristics and optimizer, we don't know the exact mathematics how this IO optimization works. But we know what kind of input has what kind of impact. Whether an input has a directly proportional impact or an inversely proportional impact, that we know. So with a greater lead time, I will have bigger safety stock. With a pathetic error CV, I will have a higher safety stock because the system thinks that my forecast accuracy is just screwed up and I need to basically have more safety stock in order to maintain this uncertainty. Similarly, if my lead time is not accurate or there are variances in lead time, it also takes that into account, and based on that, it generates the recommended safety stock. So, in a way, this is how the safety stock runs and how it generates numbers. Now, these are the numbers that are supposed to be published to supply primarily in the inventory target key figure if you are planning to move stocks or recommended safety stock into IBP, or even you have the option to give the input in terms of days so that the system looks into the future demand and accordingly generates safety stock. But whatever the results are coming, the results are not just blindly copied to supply, because inventory optimization is all about simulations. Planner does a lot of simulation by decreasing error CV, by decreasing TSL, and check multiple things. For example, in many organizations, they get a safety stock target not in numbers but in dollarized value at an aggregate level. So once the safety stock is generated, they try to see what is the dollarized value that is coming at an aggregate level. If it is higher, then they reduce the proposed safety stock at a higher level in such a way that they meet their dollarized financial target for inventory optimization. So this goes through multiple approval process based on which the final numbers are then published. Word of advice from an IO experience that I have done in my last three implementation is, You cannot do it right the very first time. The objective is to keep it simple so that the planner can get a grip of how the system is working. Then they do simulations, puts adjustment, and even requests for additional features based on which that will enable them to do multiple modification and approval process and then pass on that inventory optimization result back to supply. So this is what I intended to cover based on my experience that I have done for the past 2 years on 3 different inventory optimization. I hope you like this video. Please feel free to share your feedback and comment on this. Thank you.